Hi, y'all. So this is the last lecture for this particular module for what we're calling, I guess, Chapter 20. Although this is on Section 21-3. This is the last lecture for the current week's homework. So let me go ahead and pull that up. This specifically is going to focus on transformers. But before we talk about transformers, we have to talk about something called mutual inductance. And what we have here is a couple of different coils of wires. We've got what's called a primary coil and then a secondary coil. So primary coil is right there, and of course secondary coil is right next to it. That primary coil is hooked up to some kind of power source. So this could be, let's see, it says AC generator there. So I mean, this could be a windmill, could be a coal plant, could be whatever. Could be, honestly, could be just 120 volts AC out of your wall that we could be talking about here. So at any rate, there's an AC power source hooked up to this primary coil. And what does that mean if we've got AC? It means that my current is constantly switching back and forth in directions and also sizes. Um, so as a result, what's going to happen? The magnetic field that's generated by this AC power source by the primary coils there is constantly going to be switching. Um, as the current through that AC line changes, the magnetic field that it generates is going to change, both in size and in direction. So then what happens as a result of that? Well, as a result of that, we've got a change in flux through this secondary coil. So we've got a change in flux right there through that secondary coil, because of the fact that the magnetic field through that secondary coil is changing. And then, because we've got a change in flux, what happens? Well, we end up with an induced EMF. An induced EMF, an induced voltage, an induced current in that secondary coil. This is the background, or this is the idea of how a transformer works. So the purpose for having a transformer is to increase or decrease an AC voltage. And that's very specific there. This has got to be an AC voltage. Why does it have to be an AC voltage? Because if it were DC in the primary coil, then the current wouldn't be changing at all in the primary coil. And if the current in the primary coil isn't changing at all, then the magnetic field created by the primary coil isn't changing at all. And if the magnetic field isn't changing, then there's no change in flux. If there's no change in flux, then there's no induced EMF in the secondary coil. All right, so what we've got here is basically a couple of coils that are wrapped around this iron core. And this AC generator creates a current in our primary coil. And then as a result of that current in the primary coil, there's basically a magnetic field that's created, a flux that's created. So this right there, that voltage from our AC generator produces this flux. Well, if we've got a really good iron core and we're working in a perfect world here, then none of the magnetic field lines are going to escape, and the flux through our secondary coil is going to be the exact same as the flux through our primary coil if we don't lose any field lines at all. Well, if that's the case, then there's a connection between these two formulas that I have circles around. The delta phi over delta t is the exact same, so we can rearrange those equations and then end up setting them equal to each other. And we've got a relationship between the voltage in the secondary, the voltage in the primary, and the number of coils in the secondary, or number of turns in the secondary, and the number of turns in the primary. And we can use this to figure out the factor by which our voltage would be increasing or decreasing. It'd be increasing if we've got a step up transformer. It'd be decreasing if we've got a step down transformer. So there's our transformer equation. It relates the voltage in the secondary to the voltage in the primary. When we know the number of turns in the secondary in comparison to the number of turns in the primary. All right. The other thing we can do is we can maybe make the approximation that, well, what happens if we were in a perfect world? If we were in a perfect world with an ideal transformer, then the power that we have transferred to our secondary is equal to the power that the primary generates. Now, again, this is a perfect world, but we know, assuming that we know an equation for power when we're dealing with currents. Power is equal to what? Current times voltage. So we can plug that in on both sides, and then we can rearrange this equation. IS over IP is equal to VP over VS. And when we do, we end up generating an equation for how the currents through both coils relate to each other. And as a result, we can set up something like this, like what's circled around there. And now we've got a relationship for current, voltage, and the number of turns. So one thing we notice, though, is that the S and the P has switched places. So if we've got a transformer that steps up voltage, it's going to step down current. And vice versa, if we've got a transformer that steps down voltage, it steps up current. All right, this says we're using the idea of, okay, well, where do we see transformers in day-to-day life? Well, cell phone charger would be one example. And I gave you guys some other examples when we were meeting in person back ages ago. It says most cell phone chargers deliver 5 volts DC. Considering the fact that these are plugged into the wall, which is 120 volts AC, what's necessary in order for the correct voltage to be supplied? Well, the first thing we have to do is we have to have a step-down transformer that transforms that 120 volts AC to 5 volts AC. And then we have to have something called a rectifier that changes AC to DC. So I've got an example here of what? Of a cell phone charger, Kindle charger, whatever. And I'm looking at it, and you guys should look at your own. I know everybody's got one. But one of the things that I see on here is it says input 100 to 240 volts, and then it's got a wavy line, kind of like that. And then it says output 5 volts, and then it's got a solid line with some dashes, kind of like this with the DC. So it says 5 volts, that DC symbol, and then 2 amps. So inside each one of these, we've got a transformer that steps down voltage, and also a rectifier that changes our power from AC to DC. All right, so given the answer to that question, okay, it says what's necessary? Well, we answered that. Now I've got a question that says, what is the coil ratio? So I want to answer that question. So when I ask that, it literally means, well, if I'm asking for coil ratio, I'm asking what is NP over NS? What's that equal to? Well, let's see. If we knew what VP over VS was, then we would be all set. Do we know that? Sure. The primary, the source of my voltage is the wall. It's 120 volts. Divided by the 5 volts, that's my secondary. 120 divided by 5 is 24. So we could say that the coil ratio is 24, or we could say that this is a 24 to 1 ratio. And that's my answer. It's a 24 to 1 ratio. Use your imagination. That says 24, I swear. That's a little better. Now it says if the charger current output is 2 amps, how much current is the wall outlet supplying? Well, let's see here. I secondary over I primary is equal to V primary over V secondary. And what are we given? This 2 amps, that's the charger output. You remember I read that off. So that's my secondary current. Okay. It's 2 amps. I know what VP over VS is. That's 24 to 1. But let's see, what am I looking for here? I'm looking to figure out what IP is. That's my goal. Let's rearrange this equation. When we rearrange the equation, what do we get? IS is equal to VP over VS times IP. Just multiply both sides by IP. Let's rearrange this equation again. I'll have IS times, I'm looking to isolate IP. VS over VP is equal to IP. What did I do there? I multiplied both sides by VS over VP to solve for an expression for IP. All right, now that I've got all that, I can go ahead and I can fill in some values here. IP is equal to 2 amps, that's IS, times VS over VP. Well, what's VS over VP? Oh, that is 1 over 24. So it seems like the amount of current that's actually being supplied out of the wall outlet is 0.083 amps. All right, that's the way that works. Okay, so this charger is one example of where we would find a transformer. Basically, anything that looks like this that we're plugging into the wall, which is things like your laptop, so on and so forth. I'm sure you guys can look around the house and find several examples. Are all contain transformers in addition to other electronics. But when I say the word transformer, well, I say the word transformer, some of you are humming more than meets the eye. But I don't know, maybe that's just me because I grew up in the 80s. Anyway, if you didn't get that joke, it's fine because you didn't grow up in the 80s. But when I say the word transformer, what do you guys probably think about? You probably think about those great big boxes up on the electric poles, right? And those absolutely are transformers. So let's take a look at that real quickly. We've got some power plant. That power plant is going to have a generator, so on and so forth, like we talked about. It's going to have an output. And if we just tried to transmit power at that voltage that the power plant was outputting, we'd end up having a lot more energy loss than will occur if we step up that voltage to a much higher voltage. Basically, the higher voltage we have in our transmission lines, the less power loss we have. Of course, kind of the more dangerous it is too, but that's why we see all this high elevation when we're looking at these high voltage transmission lines. So the higher the voltage is, the less the power loss occurs. But then, of course, what do we need? We need to actually not have, I don't know, a monstrously high voltage coming into our house, right? So we have step-down transformers to transform that high voltage down to a lower voltage. And then if you go outside and maybe you look up at the power pole near your house, you might see a little box up there too, and there's a step-down transformer right there that steps down the voltage to 240 volts that then might get stepped down inside your house as well to 120 volts. So there's some of our appliances that require 240, some of them require 120, but there's additional transformers in our houses as well. All right, I think that hits the heart of what I wanted to talk about. I hope this has been clear for you guys. And like I said, this is the end of this module, this week's homework. and I will get more stuff up and so that we can talk about electromagnetic radiation, and that will be the last topic for our class for the semester. All right. Hope you're doing well.